So this video goes over a couple of reaction type things that we were not able to get to in class on December 10th, but I'll go over in class tomorrow. So if you want to preview this, feel free. The first thing we'll mention is the different types of metathesis or double replacement reactions. We've been doing these all along, but you want to just go ahead and list the types right here. So we have precipitation reactions, which you have been writing net ionic equations for these. So we can complete this precipitation reaction by switching the ions, and we'll get Ag2CO3 plus NaNO3. And based on the solubility rules that we know, sodium group 1 salt is aqueous. Nitrates are aqueous right here. This is aqueous, and this is our precipitate. And we would have to be told this in order to be able to label it. And then we just need to be able to balance this, and we're done. So that's a precipitation reaction where we form a insoluble ionic compound, this precipitate here. So our net ionic will be the formation of the precipitate, which is this. So we know that on the right-hand side, the products, we should get the solid. And the ions that create that are 2Ag plus aqueous plus CO3 2 minus aqueous. So those combine and form this precipitate. The second type of double replacement reaction is when you form a weak electrolyte or a non-electrolyte. And the probably the most common example of this is the formation of water. You could also form a weak acid. So this type of double replacement includes acid-base neutralization reactions, where an acid reacts with a base and forms water and a salt. So an example of this, here we have hydrochloric acid. This is a strong acid. This is a strong base. Okay. I usually abbreviate strong acid and strong base as SA and SB. So when we react these things, again, it's a double replacement. Our positive ions are going to switch places. So we have, let me put in my charges to help you. This minus plus. So we have H plus goes with OH minus. This creates HOH, or this is just H2O, plus calcium with a 2 plus charge. So we need 2 chloride ions. Okay, and so this is liquid, and this is going to be aqueous, but we, again, you'd have to be told that these are strong acids and strong bases, so they're considered completely soluble, completely dissociated. They're aqueous. And then if we look at the net ionic equation for this, for any strong acid, strong base reaction, the net ionic equation is always going to be H plus OH minus forms H2O, water, or HOH. Sometimes people like to write it like this to see the ions that combine. So that's our net ionic here. Let me put in my states of matter: aqueous, aqueous, and liquid. So that's what drives this reaction, the formation of water. The third type of double replacement, these are kind of specialty gas formation reactions. This you have to know, okay? Carbonic acid, when it's formed, will immediately decompose into H2O and CO2. It does not like to stick around. It just breaks up and separates into these two things. So here we have a double replacement. Okay, now this is a little bit tricky because here this acid, this acetic acid, is written in an organic fashion where the H plus is on the end. So you might not recognize it unless you, well, you should memorize that this is acetic acid. So it's often written this way too. Okay, but it's a double replacement. And so here, let's put in our charges again. This is minus, plus. When we do the double replacement, we'll get NaC2H3O2, okay, plus H2CO3. But remember, this does not stick around. Carbonic acid does not stick around. It decomposes and forms CO2 and H2O. So whenever you end up writing that, you should immediately replace it with these things instead. So here, this is a group 1 soluble salt. This is aqueous, completely dissociates. This acetic acid is a weak acid. We will work more on this later, but this weak acid, it's aqueous but will not dissociate. This is a group 1 salt that will completely dissociate. CO2 is a gas, H2O is a liquid. So when we go to write the net ionic for this, okay, and we will work a lot more on this when we get to acids and bases, we're going to be writing 2Na plus aqueous, because that completely dissociates, plus CO3 2 minus aqueous. This we do not dissociate. It's a weak acid, so we have to keep it together. So I will write it as HC2H3O2. Okay, remember these two things are the same. It's aqueous, but it does not dissociate to a large extent. This is a group 1 salt. We'll dissociate that. Oh, and I should check that this is balanced. This should have a 2 here, right? And we should have a 2 right here. Okay, now it's balanced. So let's go back and fill that in there. So here we have 2Na plus aqueous plus 2C2O2 minus aqueous. Gas, we do not dissociate. Liquid, we do not dissociate. Okay, so when we look at this, what cancels out? The Na plus is a spectator ion. Okay, and nothing else cancels out. So the net ionic here is CO3 2 minus plus 2HC2H3O2 aqueous forms 2C2H3O2 minus aqueous plus CO2 gas plus H2O liquid. Okay, so there's our net ionic reaction. Here we have a gas formation reaction where we form H2S gas and NaCl. Okay, so here, if this is aqueous and this is aqueous, you know, this is going to be aqueous. So our net ionic is the formation of this H2S gas. So we would have, after we balance this, we would have 2H plus aqueous plus S2 minus aqueous forms our H2S gas. Finally, this last gas formation, you probably won't see this. Comes up very, I would say, the chances of you seeing this on the AP exam are pretty much nil. But it might come up as a reaction that is given to you. But here again, this is a double replacement. We will form NaCl. Let me put my states of matter in first. Aqueous, aqueous, NaCl, aqueous, plus H goes with SO3, which is a 2 minus. Let me put my charges in there. So we get H2SO3. But again, like H2CO3, this does not stick around. It decomposes into H2O plus SO2 gas. H2O liquid. Okay, so let me just check that this is balanced. We know we need a 2 here. We need a 2 here. And now it is balanced. If we want to write the net ionic equation out, we can see that we have 2 Na plus aqueous plus SO3 2 minus aqueous plus 2H plus aqueous plus 2Cl minus aqueous forms 2 Na plus aqueous, right? I dissociate all of the things that I'm supposed to dissociate. Okay, H2O liquid we do not dissociate, and the SO2 gas we do not dissociate. So I can cancel out my 2 Cl minuses. We can cancel out our 2 NAs. So here the net ionic reaction is SO3 2 minus plus 2H plus aqueous forms H2O liquid plus SO2 gas. So going on from these gas-forming reactions, we did a very little bit. I was able to do this with class 1. We ran out of time in class 2 for the group of people working on the Paradeck during class 2. So this is a basic introduction to acid-base theory. So acid-base theory, the acid-base theory that we'll be looking at the most is the Bronsted-Lowry acid-base definition or theory. There are 2 other theories of acids and bases. The one that usually in chemistry, one that we focus on is called the Arrhenius. And Arrhenius acids and bases, basically an Arrhenius acid increases the H plus in solution, and a Arrhenius base increases the OH minus concentration. Okay, so that's our basic definitions from Chem 1. The Bronsted-Lowry acid-base theory is probably the most commonly used acid-base theory, besides the Lewis acid-base theory, which we will not get into in this class. So Bronsted-Lowry acids are substances that donate H plus ions. So H plus is called a proton because it's basically just a bare proton, just a proton, nothing else. So the acids are called proton donors. A Bronsted-Lowry base is a substance that accepts the protons. So they're called proton acceptors. So you can see in this picture, here's our acid. Its proton is being transferred to the base, which accepts it. When that happens, this acid turns into A minus. These 2 things right here are called a conjugate acid-base pair. The base, the Bronsted-Lowry base, okay, has gained a proton, becomes Hb plus. B and Hb plus are called a conjugate acid-base pair. This base is a conjugate base pair with its conjugate acid. Okay, the acid turns into its conjugate base. So looking at a couple examples, we can see here nitric acid. If we look at what it becomes NO3 minus. It transfers a proton, it donates a proton to H2O. So nitric acid is the acid, the Bronsted-Lowry acid, and the nitrate ion is its conjugate base. Okay, so these two right over here, the HNO3 and this is a conjugate base pair. Wow, that's very red. Okay, then the H2O and the H3O plus. By the way, this is called a special ion called hydronium. This is another conjugate base pair. In this case, H2O is acting as, it's accepting the proton, right? It's accepting the proton from HNO3. So water is the base here. And hydronium is its conjugate acid. All right, so that's our first example. Now in this second reaction, if we take a look at what's happening, here we have this hydrogen sulfate, and over here we see that a hydrogen has been added. So in this case, a hydrogen, a proton from water has been donated to the hydrogen sulfate ion. And our conjugate base pairs are these, okay? And water and OH minus is another conjugate base pair. So here the hydrogen sulfate ion is going to be, right, accepting a proton from water. So it is the base, and sulfuric acid is its conjugate acid. Water is donating the proton, so water is the acid. And the hydroxide ion is its conjugate base. Right, so what does this mean? In the first case, water acted as a base. But in the second case, water acted as an acid. So water is one of these substances which can act as an acid or a base. It's considered amphoteric or amphiprotic, which means that it can both donate and accept protons. It's like being ambidextrous. Water is ambidextrous, can do both. All right, so now we want to identify the acid base, conjugate acid and conjugate base. So pause the video if you want and do this identification, and you can refer back to the previous slide if it helps. Okay, and if we look at letter A, we can take a look at what's happening here. It looks like these two are conjugate acid-base pairs, right? And the H plus here is being donated to the NH3. Okay, so HNO3 is donating a proton. It is the acid. Donates to the base. HNO3 becomes NO3 minus, which is the conjugate base of HNO3. NH3 becomes NH4 plus. This is its conjugate acid. Second example, we got to first figure out which way the proton's going. Looks like the proton here from hydronium is going to the Br minus. So this is acting as the acid. Br minus is acting as the base. Br minus becomes HBr, that is its conjugate acid. H3O plus becomes water. Water is its conjugate base. So let's just connect up these conjugate acid-base pairs, these conjugate acid-base pairs here. So this goes with that, and that goes with that. So a couple of strong acid, strong base neutralization reactions. We want to just complete these reactions. We've already written out a couple of these in different exercises that you've had. This first one, hydrochloric acid and NaOH. Recall this is a type of double replacement. So we have NaCl plus H2O. Strong acid, aqueous, NaOH, aqueous. We're going to assume that these are given in aqueous form, H2O liquid, and this is balanced. Here we have HNO3 plus calcium hydroxide. I need to fix those subscripts. So here, again, let's do the double replacement. So we get calcium, that's 2 plus, this is minus, plus, minus. Calcium nitrate plus water. Water is a liquid. Let's just check that we need some balancing here. A 2 here. So this will be aqueous, strong base, strong acid. A nitrate is soluble. So in all of these strong acid, strong base neutralizations, the net, as I mentioned before, is H plus OH minus forms H2O liquid. Okay, so here's our strong acid, strong base neutralization. Later on in Unit 8, we will talk about weak acid, weak base reactions, and where equilibrium will be involved. These are all just reactions that go basically to completion. Okay, and we did set up the copper mine. Okay, so that's it for the introduction to acids and bases. And if you have any questions on this acid-base theory, you can ask in class tomorrow.